In this lesson, we'll be learning about Hess's Law, which allows us to determine the energy change in a reaction from either heat of formation values or from other heats of reaction. Basically, Hess's Law says that we can build a target reaction by adding together other reactions. Just like the mole here is stacking boxes to get the reaction we want, we can stack chemical equations and combine their enthalpy values. This tells us that no matter how you get from reactants to products, the overall enthalpy change is the same. So here we have a reaction energy diagram for the single replacement reaction between aluminum bromide and chlorine gas. If you remember back to the previous unit, we saw that if the products that are a lower energy level, we have an exothermic reaction. So we can find our heat of reaction by doing products minus reactants, and since it is negative, the reaction is exothermic. But this brings to mind the question of how do we determine the heat content in the first place? How do we get the values to find the total enthalpy value of the reactants so we can compare it to the total enthalpy value of the products? So because we're always talking about a change in enthalpy or thermal content, there's been a quantity called the heat of formation that has been defined to be equal to 0. And so then that's just kind of like our baseline, and everything else is compared to that. So the heat of formation for all elements in their standard state equals 0. And the standard state is given by the if you look at a periodic table, it'll usually indicate what the different states of matter are. So for example, oxygen gas, O2, would be a gas, and that would be its standard state. If you were to talk about liquid oxygen, on the other hand, that would not be its standard state, so it would not have a heat of formation value equal to 0. And then the heat of formation of all compounds is equal to the molar heat of reaction for the synthesis of the compound from its elements. So here we have determined the heat of reaction for magnesium nitride. And then since we are making 1 mole of compound from this reaction, this tells us that our heat of reaction value is actually equal to the heat of formation value for the magnesium nitride. Since we can find the heat of reaction using these heat of formation values without having to since heat of reaction can be used to find heat of formation, that means that the heat of formation can be used to find heat of reaction without having to do all of the calorimetry experiments ourselves. A calorimetry experiment once in a while is a lot of fun, but when you have to do lots and lots and lots of these things, it gets a little tedious. Thankfully, there are scientists that specialize in determining these fundamental values for matter for us. And the reason why we can and they have tabulated all of these values. And the reason why we can make this assumption between the heat of reaction and the heat of formation is due to the law of conservation of energy. So Hess's law, in its most mathematical form, is that the heat of reaction is equal to the sum of, that's the capital Greek letters sigma, means sum of, you add them all together, the heat of formation values of the products minus the sum of the heats of formation values of the reactants. Remember, delta anything is final minus initial, so therefore delta H is going to be the final state minus the initial state, or products minus reactants. So here we have an example where it is the we want to determine the heat of reaction for the photosynthesis reaction where we're making glucose. And using Hess's law. So then you just go and you look up the heat of formation values in a table. So Hess's law for this one would be products minus reactants. So we have 1 glucose and 6 oxygen minus the sum of 6 carbon dioxide and 6 water. So we look up the values in the heat of formation tables. The heat of formation of oxygen is 0, which is why it's not shown in this green box. We plug the numbers in, and we determine that the heat of reaction, in order to synthesize glucose using the photosynthetic pathway, is positive 2,826 kilojoules per mole. So this is why plants do what they do. It's a way for them to store an awful lot of energy that they got harvested from the sun in their chemical bonds. So here's another way that you can do it. You can have the combine different heats of reaction. So here we're trying to find the heat of combustion for ethane. So our target reaction is we got 2 ethane plus 7 oxygen gives us 4 CO2 and 6 H2O. And we are given a couple of different reactions. So we have 3 reactions in total. And so what we want to do is find a way to combine these 3 reactions so that when we add them together, they will add up to be the same as the target reaction. So the first thing we see is that reaction 1 doesn't have enough oxygens. So we're going to multiply by 2. So we multiply the entire reaction by 2, which means we're going to multiply the heat of that reaction by 2 because enthalpy is an extensive property. Reaction 2 is going the wrong direction because we have C2H6 here as a product and we really want to have it as a reactant, and we have the wrong number. So we're going to flip the reaction, change the direction of this reaction, which means we're going to change the sign on the enthalpy value and multiply by 2. Going on to the next page. So we have our first reaction and we have our second reaction that we flipped and multiplied by 2. I'm going to add those 2 together. So now we can start canceling out like terms. Just pretend or imagine that the arrow is like an equal sign. And just like with algebra, if you have the same term on opposite sides, you can just cancel them out. So that the C2H4 on the reactant side is going to cancel out the C2H4 on the product side. We still don't have enough oxygens, and we need to get rid of the H2 because that H2 does not show up in the target reaction. So we're going to add in that last reaction equation, and then we get rid of like terms, or cancel out terms as much as we can, and we end up with our final reaction, which is exactly the same as the target. Now, since we added those reactions together after making those corrections, and we got our target, that means we can find the heat of reaction by combining the different heats of reaction. So 2 times negative 1323 plus 2 times 137 plus negative 242. And we get that the heat of combustion for this is negative 2614 kilojoules. It is a good idea to do a reality check. Say, all right, this is combustion, so I know it has to be exothermic. It was negative, so that means that we had everything all put in the right place. All right, so that's it for the Hess's Law. So our wrap up. Our delta H values are path independent. It doesn't matter how you get there as long as you end up with the products minus the reactants. And that's due to the fact that the conservation of energy. We saw that rather than having to do all the calorimetry experiments ourselves, we can use tabulated heats of formation values, which is the delta HF, to calculate heat of reaction without having to do the experiments. So the heat of reaction, and my N should be subscripted, I apologize for that, is equal to the sum of the heats of formation of the products minus the sum of the heats of formation of the reactants. And remember, if you're going to combine different heats of reaction, you can multiply them or you can flip them around. You just have to make sure that you change your enthalpy value in the same manner. And then you just add together the modified reactions to get the total enthalpy change for that particular reaction. So that's it for Hess's law. Thanks for listening.